Hi, in this video I'm going to share how I trained a policy model for this humanoid robot that I designed in Onshape, and after exporting it to IsaacLab, I've trained it to walk like this. So they spawn in random direction with random joint angles and velocities, and they turn towards the camera and they walk towards the camera. So in my last video I explained how to train a legged robot to walk. So in this video it will be just an extension of that method with a slightly more care and a little bit more planning. So I hope you've seen that video first before you watch this video. The robot is designed around these two motors. These are made by LKM Tech. The big one has a peak torque of 80 newtons, and the small one has a peak torque of 40 newtons. The robot itself has 5 degrees of freedom per leg and 4 degrees of freedom per arm, and an extra joint around the waist here. So I've color-coded the motors in red, so you can see the big motor is, well, these ones, and the small motor there is right there. Now, some humanoid robots have 6 degrees of freedom per leg, so the ankles can rotate along the forward direction, so it can rotate left and right, basically. For this example, I've decided not to do that for simplicity and still try to get it to walk, and it seems to work. So here's the robot exported out as a URD file, and if you don't know how to do that, please watch my first video. The first thing I did is apply limits to each joint so that it doesn't move in an unnatural way. Ideally, we want the robot to learn how to walk like a human would, so the first thing I did was limit the joints in ranges that a human would be able to move the joint. So once the limits are set, the limits are set inside the URD file, and once that's set, I've imported it into IsaacSim, and then I saved the USDF file ready for training. Now, the SpiderBot in the last video was trained by following an animation that looked like this, and this was generated simply by programming the feet position and then calculating the joint rotations using inverse kinematics. So I also have to generate a similar walking animation for the humanoid robot. So here's what it looks like, and I'm going to explain next how I got this. So technically you can go on the internet and find a walking animation, but in my case I'm just going to manually get the motion capture data and then put it on the robot. So the first thing I did is I've taken 2 cameras and I calibrated, stereo calibrated the 2 cameras, and then I've recorded myself walking in my house. So this is camera view 1. I don't have a lot of room to walk, so I can only get about 2 good steps in. And this is camera view 2. Okay. So the idea is once I take the key points from this walk animation, I can get the joint angles from those key points, and then I can apply it to my robot. So here is the key point estimation. I'm using MediaPipe for this, and so you can see the key point estimations shown in red here. We have the second angle right here, and as you can see, this is running on CPU, so it's not a very good or accurate key point estimator, but it's enough for this example. So once we get the key points, we can take a look at the there we go. So here is the here is myself walking in my house, and I have the key points as in 3D space. So once I have the key points in 3D space, I can calculate the joint angles. So here is what it looks like. So here we can see each joint, well, the joints are defined with the x-axis pointed forward, and the program outputs the joint angle for each joint as a quaternion for that joint. And it looks something like this. Now, one thing to notice is that while it's stopped straight, you can see there is some errors with the post-estimation. So this means we have to do some post-processing to fix some of these joints. So now, if you want to follow along, then the programs I used for this part is, well, I have a stereo camera calibration package for if you need to calibrate your cameras. This package is for estimating 3D pose in key points in 3D space. And I also have a package for calculating joint angles from the 3D key points. So here is the joint angles applied to the robot. I take each rotation direction and I apply it to the corresponding motor, and it looks like this. You can see it's not very smooth and has, well, multiple walk cycles from which I have to take a single one out. So that's done simply by specifying a few frames that I want to loop over. And so here is a walk cycle that's cut from the key points data. And this is what it looks like. You can see it's a little bit jerky and not very smooth. So the next step is to post-process this. So after some post-processing, the walk cycle looks like this. It's much more smoother. What's changed is I've reduced the rotation on the waist a little bit, and I've looped the walk cycle by matching the derivative of the first and the last frame so that it interpolates smoothly between the first and last frames. And yeah, that's pretty much it. So now we have a walking cycle that's captured from 3D data. So before we move on, I want to say a few things about stiffness and damping. In the H1 robot, if you look at the available environments, we have the H1 and the G1 here. The H1 in simulation uses a stiffness value of 150 to 200 and the damping of 5.0. And if we look at the G1 here, it uses about 100 to 200, a little bit less on the damping. So for sim to real transfer, we really have to get these values correct, because these are really defining how much torque that can be output from the actuator. And but in most recent works, we don't really set these up like this anymore. The state-of-the-art robots use something called actuator nets. So it's based on this robot learning in this paper, learning agile and dynamic motor skills for elect robots. And the idea behind this is you take real data from your actuator, and then you train a very small network that simulates that actuator itself. So it's simulating things like the response time, the stiffness, the damping, and well, a bunch of parameters that can't be modeled in simulation. So by simulating the actuator, then when it comes to sim to real transfer, it transfers much more smoothly. So in this example, I'm simply going to use the same values that H1 uses, but in the next video I'm going to show how to actually train this actuator net using a real motor, and then how to take that trained model and train a policy in IsaacLab. Okay, so let's move on to the training code. The first thing that's changed from the last video is I've switched to using motion phase sampled from a unit circle, which was described in the paper from the Disney robot paper, and I think also from Deep Mimic. In the previous video I used a seesaw shape, so when the phase goes to 1, it suddenly drops to 0. By sampling from a circle, we have a smoothly looping phase signal. So here is the observation for this reinforcement training. Here we have base linear velocity, base angular velocity, base orientation, up projection. These are all things that can be obtained from an IMU sensor. This is the joint position and velocity, which can be obtained from the motor. So this is the action from the last step. These two observations are simply telling the robot which direction to turn and which direction to walk to. So there's different ways to do it, and in this case I'm using base angle to target and base heading projection. Additionally, I have applied a feet contact sensor. So this can be done using, in principle, force sensing resistor, which basically adds no weight at all to the robot. So you just need to connect it up and then wire it up. So I feel like it's not too much of a engineering problem if we try to implement this to the robot. And finally, we have the motion phase, which is now changed to a cyclic motion phase. So in events, the robot is being reset with random position, joint position, apply external force randomly, pushing it also randomly, and root state is also generated randomly. Now here is the reward term, which compared to the last time, quite a lot has been added. So the first one is progress, which rewards it for walking towards the target direction. A live term is this one. This one has the highest reward. Torque usage, joint acceleration, and action rate. These are regularizations, so it tells the robot to not use too much torque, not use too much acceleration, and reduce the action. So this is supposed to speed up training and stop the jerky motion that's seen in policy training. Now here is the animation tracking that was seen in the last video. It's exactly the same, and this is the new one, which is the joint velocity tracking. So instead of the joint positions, I'm also tracking joint velocities, which is just the delta between the adjacent frames. This one is move to target, just rewarded for moving to target. This is feet contact tracking. So this one, I forgot to mention, but this is tracking exactly when the feet is in contact with the ground, and it penalizes it if the feet is in contact where the animation we have the feet off the ground. So this one takes a little bit of time to generate this data, but it seems to help. Finally, I don't want it to move rock left and right, so I have a penalty for rocking left to right. I penalize it if the root is not in a flat orientation, and also for lateral motion. And finally, this one discourages the feet to not sliding the feet on the ground while it learns to walk. And other than that, everything else is exactly the same as before. So let's take a look at the training as it progressed. So here is step 0, and you can see it just falls over. All the action is completely random. And at step 10,000, the regularizer terms are working to stop it from moving too much, and so we're starting to learn how to balance. By step 20,000, you can already see it's learned how to balance, and it's trying to match the animation, so it's lifting its legs up and down to try to minimize the error between the animation and the current position. So at this point, it's getting much better at balancing, and main issue is it's sliding the feet, and at around 40,000, getting a little bit better, I guess. Let's jump up to 80,000. Yeah, so now it's learned how to turn and kind of slowly walk towards towards the target direction. At around 100,000. Oh, that was a nice catch. Anyway, it's learned how to walk like this. And let's jump to 150. Yeah, so by around 150,000, it's kind of walking by following the animation. And I don't really remember how long it took to train this. I just started it and then I went to bed, and it was trained in the morning. So I didn't use curriculum in this example, but mostly because I had spent a lot of time tuning all the weights in the reward function, so I didn't really need it. Okay, so that's it for this video, and just one thing I want to say is, although today I showed it like it was easy, but reality is it took a lot of tries to get this to work. In fact, the early attempt was to just get it to stand up straight, and that took a little bit to figure out what was wrong with my model and how to. I guess this one is very good. Maybe this is resumed training. So we can take a look at maybe a failure. Maybe this is not a failure. Yeah. So the problem is, you have these jerky motions and arms straight up, and figuring out what's causing this took a lot of time. But once this was figured out, then it was just a matter of tuning the weights until I can train the model without a curriculum. Okay, so that's it, and thank you for watching. And in the next video, I'm going to do more practical things, like training the actuator net. Okay, thank you very much.